Video 31 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is Molecular Electric Fields and Field Gradients. So far we have only looked at moments and induced moments, moments of the charge distribution of a molecule and induced moments. In this last part of chapter 4, we want to look now at the charge distribution in a molecule in a different way. We want to look at what kind of electric field or electric field gradients this charge distribution generates at some point within the molecule. So we're going to look at the electric field or components of the electric field. This is again a vector, so we have 3 components, or at the 9 components of the electric field gradient. The charges which give rise to these field and field gradients are the charges of the electrons and the nuclei, and we're going to look at the value of this electric field and electric field gradient now inside of the molecule. Going back to the expressions we had in the beginning of this chapter, the electric field is then, here we have our molecular charge distribution, and it's this kind of integral over the charge distribution, and the electric field gradient is obtained as the derivative of this expression, which then gives this expression here. We have again the charge distribution of our molecule. We could look now at the value of this electric field at the position of one nucleus, where of course we have the contribution from all the electrons, but then only the contribution from all the other nuclei. Now this electric field at the position of this nucleus K, for example, that of course will give rise to a force acting on the nucleus K. Here the force acting on K, because the force is just the electric field times the charge of the particle on which the electric field acts. Now this force of course would move, would try to move that nucleus. And that means if our molecule is in its equilibrium geometry, then of course this force acting on that nuclei would be 0, like the forces on all the nuclei would be 0, which means that the electric field at the position of the nucleus then of course would be 0. And generally the question is now, can we measure the electric field at some positions in the molecule, the electric field or the electric field gradient? First slide here. The electric field gradient is an integral over the charge distribution of a molecule multiplied with this term here. So it's very much like an expression like the electric dipole moment, which was also an integral over the charge distribution, and then just a position vector here, which means we can calculate. Now we have so far always looked at it in the different way. We looked at moments which we measured by applying fields, or quadrupole moments by applying field gradients. But of course we can turn that around. So we could measure the value of an electric field if we, at some position, if we can bring a dipole moment at that position and measure then the change in the energy of that dipole moment. Now of course we cannot bring dipole moments or quadrupole moments in a molecule, so we have to use what is there. And that is, so we only can measure those fields at the position of the nuclei. But nuclei do not have electric dipole moments. Some nuclei, however, have electric quadrupole moments, and that's the nuclei which have a spin quantum number larger or equal than 1. They possess an electric quadrupole moment. So, and with that electric quadrupole moment, we actually can measure then the electric field gradient at the position of that nucleus. And that is called the quadrupolar coupling, and here is the effective spin Hamiltonian describing this coupling, where here's the nuclear spin operator, and here we have the nuclear spin, and here we have the electric field gradient, and here we have the quadrupole moment of the nucleus. Now the product of the quadrupole moment of the nucleus and the ZZ component of the electric field gradient at the position of the nucleus divided by h bar, where the ZZ component is the largest diagonal component of the electric field gradient tensor. This product is called the nuclear quadrupole coupling constant. And experimentally one can measure this product, for example, from the hyperfine structure of the rotational spectra, from quadrupole splitting of the lines in Möbius spectra, also from the line width of the lines in NMR spectrum. So one can experimentally get the product of those two. If one then also knows the nuclear quadrupole moment, then one can experimentally determine the component of the electric field gradient at the position of the nucleus. In addition to this largest component, one can in some experiments also determine the so-called symmetry parameter, which is defined in this way, where the alpha and beta components are the two smaller diagonal components of the electric field gradient, and the CC component is again the largest of the diagonal components. Now remember, from make the same transition to quantum mechanical expression as we've done for the electric dipole moments, and therefore we get an expectation value here, where we have here electronic coordinates, and we got in the Born-Hauptmann approximation, we get also a nuclear contribution, which essentially has the same form as the electronic contribution, but it's just evaluated with the fixed nuclear position vectors here. And we can then also, the expression here is then just the expectation value of this operator, define corresponding operators, where, so we can define an electronic electric field gradient operator, O theta, and the corresponding nuclear operator, which is then omega theta, which essentially is the same, except that now summing over the electronic position vectors relative to the observation point, which is here the position of nucleus K, which means that that here actually should be K, that should be K, and also this should be K. And here also we have a sum over all the other nuclei, then K here, and again the distance from the other nucleus to the nucleus K again. So also here this is K. And then we can express a component of the electric field gradient evaluated at the position of nucleus K, just as the expectation value of this electronic electric field gradient operator and the constant contribution from the nuclear electric field gradient operator.